So, good afternoon, everyone who's here in our conference room and to those listening online. Welcome to today's seminar. Very pleased to have you here with us. Today, we're happy to have Professor Karen Lian visiting with us. She's an associate professor at the Department of Materials Science and Engineering at the University of Toronto. Her research interests include high-performance electrode materials, polymer electrolytes, or electrochemical capacitors, hybrid energy systems, and flexible printed electronics. Prior to joining the University of Toronto in 2006, she was a distinguished member of the technical staff and manager at Motorola Labs, where she conducted and led research in energy storage, RF, MEMS, and microfluidics with advanced printed wiring board technologies. She has published over 70 papers in refereed journals and conference proceedings and holds 35 issued U.S. patents. So we're very pleased to have her with us to give a presentation on her work today. Thank you.
Thank you very much for the introduction, and thanks for coming. And today it's my pleasure to introduce some of the works that we've done in my lab, which is Flexible Electronic and Energy Lab. And so before I start my talk, I want to just give you an overview of what we have done as a whole in the lab in terms of the electrochemical capacitor. So before going through that route, let me just quickly talk briefly about the electrochemical capacitor or supercapacitor. So what you see right now on the screen is a Ragone chart, shows the landscape of the energy density and the power density of the energy storage. And here you see the capacitor takes, which is on the right side up there, and is a very high power device, so it can dump the power, deliver the power very fast, but doesn't store lots of energy. And on the other side, on the lower right corner here, and you see the batteries and fuel cells, they store lots of energy, but they cannot deliver as fast as sometimes you want. So the supercapacitor is actually, in that sense, bridging those technologies, so deliver relatively high power and also store relatively high energy than capacitor, for example. And there are lots of applications out there, and here are just some of them, talking about anywhere from backup in the power station to hybriding with, for example, most of the time with energy generation device. So the energy storage and energy generation goes hand in hand, and so that it's something that can be generated during the daytime, like from solar power at night, and the energy storage can be used to deliver the energy. And also the power electronics, and also in terms of many of the applications in the transportations. So these are the general kind of view of supercapacitor and where they applies. And if we want to look inside what supercapacitor look like, and here's the device. So in general, what you see is very similar to batteries, that it has anode, cathode, and have, in terms of most of the time they are very similar. So they're symmetrical, meaning the anode and cathode are the same. And they have a separator and with electrolytes soaked into, so that being stored in a can, and they have to be mechanically sealed for leakage, that kind of problems. And so each device is normally, each cell is one device, so that you can, if you need a high power, a high voltage, then you have to use the electronic to put them together through serial parallel, like this, become a module. So this is the kind of general idea of supercapacitor. And the next thing I want to show you is what we do in our lab in terms of efforts in the supercapacitor. It's something we call EC, electrochemical capacitor. And we look at the three different efforts in three directions in our lab. Based on what we see in the previous picture, we show the electrodes. So we work on electrodes, electrolytes, and then we work on applications as well. In terms of electrode, and we know that most of the time activated carbon are the main material that's being used. And in our sense, we are not working, we're not making the carbon material, but what we do is try to chemically modify the material. So we work with Professor Yuri Gogotsi from Drexel University. So he provides some very interesting carbon material, very high performance, and then we use chemical methods to modify, to add additional capacitance to the material to increase the energy density. We also look at the direct metal transformation to make the material directly grow on the current collector. So these are the efforts on electrode side. And in terms of electrolyte, we were looking more into solid polymer electrolyte. This is going to be my focus of the talk, so I'm not going to go through detail. Also, if we have good material, it's really important to be applicable in the device. So this is actually very important to us to see where the device, how they can perform. So all my students work on the device assemblies very closely. All their material has to be tested, to be tested and verified in the device. And in addition, we're looking at working with different faculties in terms of looking to hybrid, like modeling and prediction for how the device is going to last through artificial neural network or through some of the very detailed DFT work to look at the thermal effects of the electrolyte. So because most of the ECE people, they were professors, they were looking into how to abuse the device. They want to look at, can I apply 100 amps in a very short time? So these kind of devices, these kind of data are not readily available, so we go through quite a bit of simulation with them. And also, the other efforts is with the solar cell hybridization, we call solar cap, so that we actually are using the solar cell to charge the capacitor and then make a solar for the self-assembly, self-powered units that can be thrown in the field, that you can use the solar panel to charge the capacitor and use the capacitor to pulse some of the signals that can be transferred back to the central nodes. And so these are kind of efforts overall that we're looking at. And today I want to focus on one effort, which is the solid polymer electrolytes. So this is my talk. And so I want to give you some of the recent advance on the polymer electrolytes, and then look at it especially for the ultra high rate performance. So the outline of this talk is pretty much into the following. So I will start with some background and then look at the ionic conductor that we'll be using, which is hydropoly acid, and then we'll look into the polymer electrolyte, how we develop these, and then I will look at the several different types of devices that enabled by these type of polymer electrolytes, and then we'll look at alternatively how to expand the cell voltage window and with different kind of strategy that we'll be working on, and before I summarize. So the key words of this talk is high rate and flexible solid devices. So to start looking into high rate, most of the time the electrochemical capacitor has been developed by focusing on looking to how to improve the energy density, meaning increase the capacitance. Look at how many farads per gram, which is important. However, as we see in the first slide that I showed, that in the Ragone chart, the electrochemical capacitor also have a very important function, is that it can deliver high power. So this is something that has been neglected for a while, but recently, starting about 2010, they start to have more and more efforts in this field. First started with, at that time, Patrice Simon and Yuri Guguzzi's group, and looking into using onion-like carbon, and they published the paper in Nature looking into that they can deliver 100 volts per second, that kind of high rate. And by the way, this is a CV, and for those who are not familiar, you are looking for a rectangular current voltage response, and that's the one that shows the most capacitive behavior. So this is something that's been published to show that it shows 100 volts per second, which is a very, very high, fast rate in terms of when you scan the apply the voltage, and then the current can respond. And so in that case, we got about 0.9 millifarads in this rate. And later, in the almost the same time, John Miller also published the same paper in the same time in Science, looking to using graphene and was able to deliver at about 120 hertz in terms of the rate for delivery, so it can be used for filter now. So this is another very high rate type of application. And you further, so this is at 120 hertz with 90 microfarads. And they're using KOH as electrolytes. And these kind of efforts demonstrated, yes, supercapacitor can go very, very high rate. So that sort of inspired many more papers and applications this route. So this is another paper that published talking about they have using reduced graphene for 400 volts per second. And then there are other different type of graphene going for also very relatively high rate. So all of these, what I'm showing here, for the recent development for the high rate application, they all have something in common. They are using very highly advanced electrode material, unlike carbon, those are nano diamond, graphite nano diamonds, graphenes, and also they have another thing in common. So other than they have advanced electrodes, they are all using liquid electrolyte. So the liquid electrolyte is good because they always have the highest conductivity. However, they sometimes will have some limitation in terms of applications. So in our case, what we want to do is looking at using flexible, rollable devices so that we have to use solid polymer type of electrolytes. So here, I want to give you one example. Why do we want to use a polymer electrolyte? So this is, for example, a device that we have made, actually it was a long time ago, and we can actually try to wrap around the battery. So it doesn't take any space, but now the device itself is a hybrid device, has battery and a capacitor together. And with this device, the hybrid device, we have done some tests in terms of high pulsing, so for high rate type of application. And what you see here is on the left side, you see the two graphs here. One is battery only, so it's constantly pulsing at about 2.5 amp current, and then you can see it's pretty much died at a cutoff voltage of 0.9 volts at about 20 minutes. However, even with this very thin, flexible device, which only has about 25 millifarads as a device, and what you see is the hybrid shows a much longer cycle life. And actually, it's sort of killed, it died about 84 to 5 minutes. So the ratio of this with and without is about 4 times more in terms of the energy delivery. And this effect gets even more pronounced when you look at the right side of the curve, right side of the slide. Here, the current gets bigger. Of course, the battery dies faster. However, when you see the hybrid, when you look at the ratio now, it's 5 times. So the more the higher pulse, the better, or the more pronounced the effect you will see the hybrid that when you have a high capacitor that is involved. So these are kind of things that capacitor not only can work alone, but I think more importantly, they can actually use in the hybrid system to help the battery to last longer. It doesn't mean that battery actually has a longer life. It just more effectively utilize the battery capacity. So did I press? Yes. Okay, so that is our goal, so that you see the effects of if we can use flexible device to roll around the battery. And so to enable to do that, we basically have to look at what the current capacitor are, and then we have to abandon some of the current package ideas. So like currently, this is what we just saw, right? We have the electrolyte liquid and the soak and the pack. So we really have to abandon this idea by going through a different route. So we're looking to polymer electrolyte in this case. And so with the polymer electrolyte, it can act as a glue, but meanwhile with ionic conducting, so that we can have not only flexible device, actually more important is that we can really not having these dead weights in terms of packaging, so the energy density can be increased, and we can actually use these kind of configuration. So in this case, we can stack, because they are dry, we can stack the electrolytes, and then using the bipolar structure so that we can stack multi-cells in one package so that we can further reduce the packaging of the devices. So this is the kind of goal we were looking at. And this idea of gel electrolyte, the polymer electrolyte, is not new. And actually way back, when I was still in Motorola, we've already patented some of the devices that we made. This is actually a 1 cell, 4 cell, and a 8 cell device that for electrochemical capacitor that goes through the stacking kind of form. And then this is using a kind of gel electrolyte I'm going to talk about. And recently they also made more papers looking into similar type of gel electrolytes here in the stacking so that they can be thin and flexible, they can be even bent. And all of these devices have one thing in common. They're using polymer gel electrolyte, which is PVA with phosphoric, polyvinyl alcohol with phosphoric acid. This gel electrolyte is very useful and was invented actually, I think, in 1985 by Tony Pollock and Alison Buehler from Ally Signal. And this material works really well. However, since it's a gel, there are some issues in terms of aging and also environmental stability. It will dry. It works really well at the pristine stage, but over long term it gets dried and the performance will decay. So what we want to see is how to find some material that is working that works well in the solid states. So here's what we're looking at. The candidates is the hydropoly acid. And hydropoly acid has one unique feature, is that it has a high proton conductivity in the solid state. So these are kind of conductivity that was measured in their salts form. So this is really something very useful. And then they are very low cost. And then they have their salts, actually, they have less aggressive chemistry, and also they have been used in many other applications like fuel cells and sensors and so on. However, you may also consider, for those that are familiar with this material, there is a problem because this material sometimes has been used as, for example, active material. They can actually use to modify the carbon or modify the electrode, adding redox reaction. So why can this be used as an electrolyte that cannot have electrochemical activity but just ionic conductivity? So this actually, the answer of this is really coming from this graph, which is shown, which is published earlier in 1975. But what's interesting about this graph is showing you that in the hydropoly acid form, which is in here, and in here, let me just take a step back, look at, so in hydropoly acid, you have a heteroatom in the middle, and then you will have surrounded by these pink ones are the transition metal ions and the oxygen, so form a cluster of a special stable structure. And so this graph, what it shows is by changing the heteroatom in the middle, you actually reduce or change the first electron reduction potential by going this way. So from phosphorus to silicon to boron, you actually, the first electrochemical reaction will occur, the window starts to going more negatively. What does that mean? Let me show you some of the graphs that we've done in the lab. So in this case, we started with sulfuric acid, which is a standard, well-known electrolyte. And by looking at the phosphorus tungstic acid and the silicon tungstic acid, you see the first reaction, the voltage window has been pushed towards the negative range. And then when you look at here, the black and the red, which is phosphoric acid, sulfuric acid and the SIWA are very, very similar. That tells us that within that range, it is safe to use SIWA as an electrolyte. And so this is something that based on what we have done at the first 3 electrode tests, and then to further analysis and to prove this point, we developed the liquid beaker cell to prove this point. And here are some of the results. This is results of, as we said, we're looking for a very rectangular shape photomogram. And so these are 3 electrodes, one electrode in 3 different electrolytes. Started with sulfuric acid, the standard one, which is the black one, and then we look at the tungsten, phosphor tungsten base and the silicon tungsten base. And what you can see, the red one here shows a little bit higher activity, which is, if you go back to look at it, it's the tungsten base. We see there's a little peak here. So that's why there was a peak here in the tungsten case. So that, however, if we look at the silicon versus phosphoric versus sulfuric acid, they are pretty much overlapped. So that means it is reasonably safe in this window to use this material. And we further look into a different type of material. In supercapacitor, there are two kinds of energy storage mechanism: double layer versus pseudocapacitance. And pseudocapacitance, the best gold standard is ruthenium dioxide. So we look at the ruthenium dioxide. Again, we see a very nicely shaped square that sort of tells us that yes, the material, the solution is safe, the electrolyte is okay to be used. So with this in mind, so we start to develop some of the solid electrolyte material. And the problem now we run into is that for the HPAs, they are salt, so they cannot form a film. So this is something that we have to look into, and all those results that I showed the table that the conductivity was actually done through a pellets. So, you know, in order to make it become more viable to the device, we have to look into that problem. The second problem is they are soluble in water, so they are very sensitive to the moisture in the environment. So these are the things that we need to overcome. So the way to do it is using polymer electrolytes. And for a good polymer electrolyte, we were looking for high ionic conductivity at all temperature range and high stability and good shelf life, especially for supercapacitor that you have to be used in room temperature and for a long time, for long cycle lives. And so with that in mind, we're looking to polymer to immobilize these HPA, and also we add different type of additives to overcome some of the shortcomings that I've just talked about. So in our case, I'm just going to show you some of the development that have been done, primarily looking into, we have three functional groups to begin with. One is the polymer matrix, and this is what polyvinyl alcohol was used, and we use very small amounts. So the majority of the electrolyte actually is these silicon tungstic acid, SiWa, and so this is our ionic conductor. And in order to further improve some of the conductivity, we also have introduced some of the smaller molecule additives for different purposes that we're going to talk about. So we have a few generations of electrolytes, and so primarily we focus, our material composition sort of follow this kind of the rule that mostly we don't have more than 10% of the non-conductive material. So we try to use a very heavy load of a conductor, so that's more like a salt in, we're more into this polymer in salt kind of configuration. And so we're looking at it to improve these kind of properties. And so we have basically developed a few generations. The first generation was just simple SiWa with PVA, two components, or we call binary system. And then we started adding a little bit more of phosphoric acid, that's what we call Gen 2, or now it's a ternary system. And then we start going to more, actually when we go to generation 3, we have different versions of A, B, C, D, cross-linking or additives and so on and so forth. So there's a list of things that we will be working on improving the properties over time. And so when we started with gel, these are more in the gel form, and in the third generation, and most of the times we're dealing with actually a membrane, a film. And so how these things can be used, how are we characterizing them, and we basically put them into a devices, a cell to test this property. And our cell assembly, let me just quickly introduce to you, started with very simple 2 electrodes, and the electrodes are thin foil metal current collectors, and stainless steels or titanium, and then we can coat different kind of active material that we want on top and to make the electrode. And we basically apply the film by painting or coating or sandwiching them, and then we just laminate the other similar electrodes, so it's a symmetrical device, so that's pressing them together, and apply the pressure and temperature, and so now we have a device. And the device itself is like this, and the thickness of the electrolyte is about 50 microns. So it's very, very thin. So that's why the conductivity can be very good. No, the cell resistance is very low. And then we can choose if we want to laminate. So the overall device is about 0.2 millimeter. So it's very thin, and that's why it's a flexible device. Okay, so this is the kind of device that we develop and also we use for characterization. So let's first look at this polymer film that we have developed in terms of their conductivity. So we're based on this material, sandwiched in between thin film, 2 mil thick stainless steel. And these are three types of conductivity that we have monitored over time. It's about 2 months time period. And look at the three types of generation. The first one, as I said, is 2 components. So it has about 0.01 Siemens per centimeter in terms of the conductivity. And the Gen 2, now we're adding a small amount of phosphoric acid. The conductivity did increase. And the third generation that we add more cross-linking agent, and the conductivity actually gets reached about 0.025. Which in terms of the conductivity, and each one of devices, each one of those data has about 10 devices. We look at the distribution. So it goes pretty much close to the solid of a SIWA, the conductivity by itself. So the conductivity increased each time that we develop with different generation. And we've also looked at a different temperature how these how these electrolytes perform. And so far, within the temperature range, we look at, this is Gen 2, Gen 3, this is 2. So this is one contains small amount of phosphoric acid. This is the cross-linked one. And they are all still within the range of proton hopping mechanism. And then you can see that, but overall, there's a huge gap between the two in terms of the conductivities. And so what we have tried also is to try to compare with the landscape, the current well-known electrolyte material. So the ones that we select was Nafion. We use the ionomer from Nafion. So we compare with that with our Gen 2 material in the same way, so that we paint them in the same way, sandwich them and made the device. And here is the comparison of Nafion ionomer versus the PVA phosphoric acid, SIW phosphoric PVA devices here. So at the beginning, the pristine condition, what we see is that it has, the Nafion looks better. It performs much better. And however, if we just leave it in the room temperature, in the ambient condition, the Nafion, the conductivity decreased very quickly. However, the material that, because it's a solid conductive in the solid state, so this is relatively stable in about 2 weeks' time. So that sort of gave us some idea that where our material in terms of stability is. And so we've done quite a bit of analysis by looking at these, look at the FTIR, we look at the TGA, the DSC, and we look at XRD. We found XRD is a very useful tool for analysis of this material. Well, as one thing we know, the most important thing, and in our HPA, hydropoly acid, is the crystal, the water, or with PVA is the water retention, because the proton do transfer over the water, and the reason we saw the Nafion has going, is the performance deteriorated is due to the water retention problem. So that we actually looking at XRD and try to identify what is the best way to monitor or tracing the water content. And what we have found is by looking at, for example, this is a solid, and this is a solid Gen 1 material that's binary, and this one is actually the Gen 3, is also solid. And what we want to look for is a few characteristic peaks here that corresponding to hydration, which is right here, and dehydration, which is this peak, and also we were looking at the Kiggins structure to make sure that we are using the HPA, which is still in the Kiggins structure range. So these are the 3 peaks that we can use to comparison, so that my student did a really detailed work looking at the TGA, how much water you have, and then basically look at the ratio of this peak versus the hydration peak with the Kiggin peak, which is a fixed peak, or looking at the dehydration peak with that peak. So we can generate a working curve to know exactly how much water based on XRD, based on the conductivity, and based on the how much, so that we can have a very good idea. And if we have a fully hydrated situation, which is the best case, which is showing here, which is showing here that these are the 2 peaks, which is the fully hydrated peak. This is actually a new peak. And we basically have no crystal structure. So the amorphous case is the best because now the segment motion is very free, and then the conductivity can reach to the highest optimum level. And so this is kind of things that we look at from the material, from polymer. I just give you a very short overview of what we characterize. And now what I want to do is show you some of the devices that once this polymer is being used in device, how do they look? I will give you 3 scenarios: metallic, double layer, and pseudocapacitive electrode. So these are the 3 cases. Let's start with the metallic. We just use a stainless steel, the very simple, basic. And in terms of a double layer, currently we are only using some mediocre graphite material. The reason is that we want to see, even with the mediocre type of electrodes, can we reach a very high performance like what advanced carbon has. Actually, I do have onion-like carbon and graphene, but I think it is really for this type of study, for our presentation, for this presentation, I would like to just show the graphite because that shows you really the effect of the electrolyte. The other ones that I want to also show is some of the pseudocapacitive electrodes that all of these are in the solid states. I will show you the ruthenium and the molybdenite. So the first example is a solid metallic double layer, so stainless steel sandwiched in the polymer electrolyte. Before that, I want to show you the 2 graphs here. The black one is a 5 molar sulfuric acid, and the green one, the red one is the naphthalene as pristine condition. These are the ones has been cycled at the 5,000 volts per second. So this is the highest rate that the machine, the potential stack can reach. And these are the 2. They look very very close to rectangular, and this is a super ultra high rate. So this is very encouraging. And this is the blue one is the polymer electrolyte in the gel situation that you've seen the previous XRD that in the gel condition. And this is actually shows even better in terms of the resistivity. It's more, it's less tilted. If it's more tilted, it means more resistive. It's less tilted, and it shows a little bit slightly more capacitance. So this is actually from the solid electrolyte, so that it can reach the liquid. It can perform equal or better than the liquid electrolytes or naphthalene. And now let's go back to the same story I just mentioned. We use the Gen 2, which is not the best material, but it can show you the story. This is at the beginning. We look at the naphthalene versus the PVA, SIWA, and a small amount of phosphoric acid. And this is the beginning, and also under 5,000 volts per second. And the red one here is our device, our electrolyte, our devices, the day 1. And the day 14 at the end, so this red one still stays, and the black one is the naphthalene. That's sort of consistent with the story I just told you in terms of the ionic conductivity, that because in the ambient condition, the naphthalene cannot sustain the water, so that the conductivity decreases significantly. So this is all at a very high rate. And then we move on to look into using the solid graphite AA capacitance. This is a very nice 1 volt per second, which shows very nicely squared, a rectangular shape, and 2.5 millifarads per second per centimeter square, and it's 10 volts and 25 and 50 volts. And up to 50 volts per second, we still can reach about 2.5 millifarad per centimeter square, which is, well, as far as we know, which is the highest capacity can be achieved at this kind of rate. Okay, so we've looked at the charge-discharge. A very nice triangle symmetrical behavior shows that it is very capacitive. And we also look at impedance. And in the impedance case, we look at the impedance using an approach that proposed by Patrice Simon's group, and by deconvolute the capacitance to real versus imaginary. The real capacitance is showing here at the very low frequency, which is the upper left in your case, which should correspond to the capacitance that from the DC, that from the CD that we just saw. The more important thing is the blue curve here, which is the imaginary capacitance. The peak at the imaginary here is corresponding to a 45 degree in the impedance. What does it mean physically is that at the higher end, it's a resistor dominating behavior, and if it's the lower end here, it's capacitive behavior. So you want this time constant to be as higher frequency as possible for the high rate. So this 10 millisecond is the highest ever being reported. So we've also looking at the ruthenium dioxide versus ruthenium dioxide electrodes, and here are the since it's a pseudo capacitive, so it has a much higher capacitance, and again shows a very viable rectangular shape. And this is about 5 volts, and this is a charge-discharge at a much higher rate, much higher current because of the high capacitance. And this is the impedance that we've developed. And of course, the capacitance, the time constant is higher now. However, consider the capacitance is RC, right? So the time constant here, by considering the capacitance versus the double layer, the conductivity actually in this cell is better than the previous cell. And we have also looked at the molybdenum. This is another capacitive material that has been reported. And here are the two electrodes that what I'm trying to compare right now is the liquid, the black one, versus the solid, which is the red one. And at the lower rate, 1 volt per second, the solid is smaller in terms of capacitance. However, when you have a higher cycle rate to 10 volts per second, and the capacitance, the liquid capacitor looks much more tilted due to the high resistance. However, the capacitor, the solid state, stays in the capacitive stage. So we have looked at even higher rates, 50 volts, 100 volts per second, and this is something that is comparable to what we have seen in the literature, but now everything is in the solid states. And in terms of, I'm going to, for the time's sake, I'm going to skip this one. It just shows the impedance, say, the similar type of story. The next topic I want to sort of briefly touch upon is the voltage window. So far, since it's a proton conductor, we're looking at 1 volt per second, 1 volt window. And for most of the electrochemical capacitors, we are looking for much bigger window that we can. So there are several strategies that we've been pursuing in our lab, using ionic liquid polymer, using asymmetrical cell, and what's the other one that I want to really talk about is the multi-cell in one package. So in the case of, for these, I'm going to skip the ionic liquid and just give you a very quick view of 2 slides of asymmetrical, and we're going to look at the multi-cell. So in the asymmetrical, it's the same way. We're using different electrodes, so the same ideas as the people design the battery, so to open up the window. By doing that, we doing the same thing that thin film and electrolytes put out, but now with a different type of electrodes, and we coat it down, and we can laminate them and just fuse them together. And the device is normally 0.4 to it's about 0.5 millimeter thick. And these are kind of the performance. By going through the asymmetric design, we can push all the discharge in the high voltage window, which is highly desirable. Now we push to about from 0 to 1.5 volts. And then this is actually a charge-discharge curve. What's interesting you can see is the capacitor capacitor behavior was up to about 1 to 1.5 volts, and then it's going down to have a very severe discharge here. So that means that these two curves show that asymmetrical, even the solid state is viable, that you can do for go for high rate. The next one that I want to really go through it quickly is the multi-cell device. So far this is what we have. 2 electrodes, electrolyte sandwich in the middle. And what we try to do is stacking to one electrode in the middle, which is called a bipolar plate. And now if we sandwich them, that we can have 2 cells or even more. We can do the same thing for carbon electrolyte. This is stainless steel carbon. So here is an example of a bipolar plate of a stainless steel electrode. Now what we have is 2 cells that stack together. This is about 1.8 volts. If you remember, previous was 0.9 volts. And again, at 5,000 volts per second. So it retains the high rate performance even when you stack them together. And we also look at the cyclability, and we only went to 20,000 cycles. This can go really fast. But what the point here is that at the 100 versus 20,000, they are pretty much overlapped. So the cycle life is very good as well. So with the same kind of idea, we apply this to the graphite electrodes. This is 1 volt, one single cell here, 1 volts per second, and this one is 1.8 volts. So this is 2 cells in the same idea. We stack them together, and then we can go from 1 to 10 to 25 to about 50. It gets a little bit tilted. However, the point here is that we demonstrate that the stacking of this kind of device can save you quite a bit of packing material, and then to increase the energy density as well. And this is just the last graph that I want to show you that when you have one device, you do have a high capacitance, but when you have 2 devices, they are in series, so you can expect it that the device should have a half the capacitance, which is the red one. However, in terms of time constant, they still stays very much the same. That shows you that even with stacking, you didn't increase the resistance that much. So this is what I want to give you, the overview of the solid electrolytes and what they can do. And so far, everything was just talking about proton conducting, but I want to just show you the recent development in our lab that we were able to look into alkaline-based film as well. And this is actually 2,000 volts in the solid device, and then with different temperatures. So if you want to look at the temperature of 20 degrees, which is that blue one, so which still shows at the 2,000, they can show a very high rate type of performance. With that, I'm going to end my talk. And primarily, the message here is that these electrolytes, the solid HP-based electrolytes, have been able to show that it can perform equal or better than the liquid aqueous electrolytes, and can be applicable in double layer or pseudocapacitive materials, and it stores energy with extremely high rates. So far, you're looking at the volts, hundreds or thousands of volts, and then you can retain the conductivity with reasonably good shelf life and cycle life as well. And more important, I want to show that multi-cell devices in one package is possible. And so with this, I think you have a very high future, very promising future for these kind of devices, for the energy storage in the future. With that, I want to really acknowledge all this work was done by my students, especially Han Gao. He was the leading PhD student with a whole bunch of undergraduate students working on that. And also, I'd like to thank the NSERC and all the funding agents for the funding for the project. And thank you for your attention.
We have some time for questions. Is there anything you want? Or if you have any on mind?
For ultra-high secondary measurements, what kind of equipment do you use?
CHI. Oh, the question is for ultra-high rate performance, what kind of equipment? The ones that really work well is CHI. I don't want to advertise it, but they're really, that's the one we're using. No, it's a 660. Yeah.
And those also compare the conductive field naturally and those of pH 8. So what temperature do you use?
The question, so shall I just repeat the question here? The question is I'm comparing the Nafion, right, with the PVA, SIWA. They are all in the ambient condition, like 25 degrees. And so basically, we made the cell, we leave it there, we left there, and then we measure actually every other day, and until 14 days later, in the ambient.
And in field cells, normally, for example, high temperature field cells, we use PV5 from the phosphoric acid
Right.
as the electrolyte.
Yes.
You try that.
The question is, the fuel cell use PBI with phosphoric acid. I tried it way back when I was in Motorola, but we haven't really used. One of the ideas of these performance is that we like to actually apply gel to begin with because it penetrates to the pores better, so that we can leverage a high. So if you start with a high film, with a film, you may lose these kind of benefit of interface. So interface actually is very important for high rate.
Can you explain a little bit more about the production mechanism for electrolyte?
Oh, okay. The question is, can I elaborate a little more in terms of conduction mechanism? Yeah, it's water. Actually, the HPA it has a lot of crystallized water, and then the mechanism so far being believed is proton hopping. So through the proton hopping through, and then there is, and I think PVA also provide extra hydrogen bond sites, so to encourage the hopping.
Is there any kind of studies taken this part?
Yes, because as you see, the conductivity is the best one we have actually so far is a 0.03 Siemens. It's not the highest, so it's proportion to the thickness. But if you can make it like, so I think 50 because we don't have separator, we just use directly the film. So 50 micron is kind of happy zone for us. Otherwise, if it's too thin, we'll worry about shorting.
So is there when you charge and discharge, is there any heat effect? Do you see the temperature increase?
Good question. No, we haven't. Okay, right now we have not. We actually have an IR camera just bought to try to look at that. But I think what happens if we have a heating effect, because this is basically you think about the glue, right? The glue two together. If there's any heating, you will have heat pocket. Then it will really affect the capacitance and the conductivity. We will see, and also that's one problem that if you use this polymer that you over abuse it, it's irreversible. You will see that.
I know PVA is not a proton conductor itself. Have you ever tried to use some other proton conductor polymer as a membrane matrix?
Actually, no, because okay, in our case, yeah, I mean, we didn't try. The question is, sorry, have I tried any other proton conducting polymer? The question is, the answer is no, because right now what happened is we use so much of HPA, so the less than 10% of polymer is basically a small binder for us in our case right now. Yeah, that would be something interesting to try, but also the other thing that we have at that time, it was limiting our look at more, is we're looking for something, most of the product now you're looking at ionomers stuff. That gets more expensive. We're looking for something really cheap to be able to do it.
And we know HPA and phosphoric acid all.
Yeah, proton conducting, yes.
They are not very stable. Even tangled polymer. How do you solve leaching problem?
Leaching?
Yeah, leaching. What out?
Oh, the question is, how do I solve the problem of leaching? So this is solution leaking out, right? Okay, the polymer actually, you see, it's very dry film, right? And we do have cross-linking, for example, to help to lock the HPA. And also, we actually recently paper was on the silica. We use silica actually also as a locking mechanism, helping to store the acid. Because the HPA is a solid, if you're looking at the leaking, it has come with some water, right? So if we store them together.
Is this HPA that you're using, is this chemically bound PVA?
It's actually blended, so there will be some hydrogen bonding, but yeah, it's not really. Yeah, it's more of a blending. Yeah.
And have you also tried this other polymer, polyethylene?
Okay, the question is if I've tried polyaniline. The question is no, because polyaniline we worry about it's electronically conducting, so it will cause leaking. So yeah. We try to avoid that, yeah.
I forgot which slide you mentioned that you will also look at the thermal properties. What does that include?
Okay, that's very early. So the question is the thermal property. Those are pretty much. Actually, I'm collaborating with. That's my first slide of what I'm doing with other faculties. The thermal is basically looking at the electrolyte interface through DFT and through molecular dynamics to look at how would you apply a huge field and how is molecules going to change in the kinetic energy and how